Hello students, welcome back to the Sciacademy. In this video lecture, we are going to discuss about the dual nature of radiation and matter, chapter 11 of the class 12 term 2. So let's start. The introduction part. The Maxwell's equation of electromagnetic jump and Hertz experiment on the generation and detection of the electromagnetic waves in 1887 strongly established the wave nature of light. So the wave nature of light was already established in 1887. At the same period, at the end of the 19th century, experimental investigations on conduction of electricity through gases at low pressure in a discharge tube led to many historic discoveries. The discovery of X-rays by Roentgen in 1895 and discovery of electron by J.J. Thomson in 1897 were the important discoveries in the understanding of atomic structure. It was found that at sufficiently low pressure of about 0.001 millimeter of the mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. The color of glow of the glass depended on the type of glass, it being yellowish green for soda glass. The cause of this fluorescence was attributed to the radiation which appeared to be coming from the cathode. These cathode rays were discovered by William Crookes, who suggested that these rays consisted of streams of fast moving negatively charged particles and that were later called as the electron. J.J. Thomson was the first to determine experimentally the specific charge, that is the ratio of charge to mass of the cathode rays. They were found to travel with the speed equivalent but less than the speed of light, that is their speed were bounded between the zero point 0.1 to zero point 0.2 times the speed of light. The presently accepted value of specific charge is 1.76 into 10 to the power 11 coulomb per kg. Further, the value of E by m was found to be independent of the nature of the material. That is, E by m value is independent of the metal, and this suggested that the cathode ray particles universality. Around 1887, it was also found that certain metals, when irradiated by UV light, emit negatively charged particles having small speeds. Also, certain metals, when heated to a high temperature, were also found to emit negatively charged particles. The value of E by m of these all particles were same as that for the cathode ray particles. These observations thus established that all these particles produced under different conditions were identical in nature, which were later, as I told you, that called electrons. And for that, J.J. Thomson was awarded the Nobel Prize in Physics in 1906. Now we'll discuss about the electron emission. We know that metals have free electrons that are negatively charged and are responsible for the conductivity. However, the free electrons cannot be normally escape out of the metal surface because they were bound, and metal surface acquires a positive charge if they were released from the surface, and because of this they were repulsed back to the metal. The free electrons is thus held inside the metal surface by the attractive force of the ions. Consequently, the electron can come out of the metal surface only if it has got sufficient energy to overcome the attractive pull. That means if you want to eject the electron from the metal surface, you will have to provide the sufficient energy more than that of the attractive forces. A certain minimum amount of energy is required to when to electron to pull it out from the surface of the metal. This minimum energy to escape from the metal surface is called the work function of the metal, and this is particular for the particular metal. That is, it is the characteristic of the metal, and it is denoted by the phi naught. And we measure the work function in terms of electron volt. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 coulomb volt. That is 1.6 into 10 to the power minus 19 joule. This unit of energy is commonly used in atomic and nuclear physics. The work function depends on the properties of the metal, as I told you, and the nature of its surface. The values of the work function of the some metals are given, as you can see that for the platinum it is highest, and for the cesium it is lowest, and for the rest metal it is lying between these two values. There are three types of emission. First is a thermionic emission, second is a field emission, and third is a photoelectric emission. In case of thermionic emission, when we provide suitable heat, the electron gets sufficient thermal energy and it becomes able to come out from the metal surface. And in case of field emission, we provide very strong electric field of the order of 10 to the power 8 volt per meter. The electrons can be pulled out of the metal by breaking its barrier, as in case of spark plug. In case of photoelectric emission, when light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface, and we will study about the photoelectric effect in details. Students, you might be surprised that phenomenon of photoelectric emission was discovered in 1887 itself by the Heinrich Hertz during his electromagnetic wave experiments. In his experimental investigation on the production of EM waves by means of a spark discharge, he observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by the UV light from an arc lamp. So, light shining on the metal surface somehow facilitated the escape of free charged particles known as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface, and they gets emitted. Halwas and Lenard's observation. Wilhelm Hahlwas and Philip Lenard investigated the phenomenon of photoelectric emission in detail during 1886 and 1902. Lenard observed that when ultraviolet radiations were allowed to fall on the emitter plate of an evacuated glass tube enclosing two electrodes, current flows in the circuit. As soon as the UV radiation were stopped, the current flowing also stopped. These observations indicate that when ultraviolet radiations fall on the emitter plate C, electrons are ejected from it which are attracted towards the positive collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in the current flow. Thus, light falling on the surface of the emitter causes current in the external circuit. Halwas and Leonard studied how this photocurrent varied with collector plate potential and with the frequency and intensity of the incident radiation. Halwas undertook the study further and connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Positive charge on a positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. So Halwas, by his experiment, observed that incoming radiation falling on the metal surface causes the electron to get emitted. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Halbwachs and Leonard also observed that when UV light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value, and that minimum value is known as the threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. Therefore, there is a certain frequency for each incoming radiation below which there is no emission of the electron. It doesn't matter how much the intensity of the incoming radiation light is. Now we will discuss about the experimental study of the photoelectric effect. So let us discuss about this experimental setup. This figure depicts a schematic view of the arrangement used for the experimental study of the photoelectric effect. It consists of an evacuated glass quad tube having a thin photosensitive plate C and source S, collector plate A. The electrons are emitted by the plate C and are collected by the plate A by the electric field created by the battery. The battery maintains the potential difference between the plate C and A, and this potential difference can be varied. The polarity of the plate C and A can be changed, reversed by a commutator. You can see here is a commutator. We can change the polarity as per our requirement. The plate A can be maintained at a desired positive or negative potential with respect to emitter C. When the collector plate A is positive with respect to the emitter plate C, the electrons are attracted to A. The emission of the electrons causes flow of the electric current in the circuit. The potential difference between the emitter and the collector plate is measured by a voltmeter V, whereas the resulting photocurrent flowing in the circuit is measured by a micrometer. It should be noted that the current flow in the circuit used to be very small, and that is measured in terms of microampere of the micrometer. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and frequency of the incident light can be varied, as can the potential difference V between the C and A. Now we'll discuss the variation of photocurrent with respect to intensity of radiation, with respect to the frequency of incident radiation, the potential difference between the and collector plates, nature of the material of the emitter plate. Different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the emitter C. The intensity of light is varied by changing the distance of light source from the emitter. So students, let us study the effect of intensity of light and photo current. Consider this figure. You can see that on the x-axis there is intensity of light and y-axis there is photoelectric current. The collector A is maintained at a positive potential with respect to the emitter C. You can see in this diagram. So this collector is maintained at positive potential with respect to this emitter C, so that if the electrons are getting ejected from this metal surface emitter, they will be pulled towards the collector A because of the potential difference between C and A, keeping the frequency of the incident radiation and the potential fixed. So when we are studying the effect of intensity of light, we will keep the frequency of the radiation and potential fixed. That means will not vary the incident radiation intensity and potential difference between C and A. So we will vary the intensity of light by how? By changing the distance of the light source from the emitter. And by doing so, we see that photoelectric current increases linearly with the intensity of incident light. So it varies linearly, right? This implies that number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. That means there is a direct relationship between the number of photoelectrons emitted per second with the intensity of radiation incident. Now we'll study the effect of potential difference between the collector and emitter on the photoelectric current. So for this, we will keep the plate A at some positive potential with respect to the emitter plate C and illuminate the plate C with the light of fixed frequency nu and fixed intensity I1. So we will keep first A at positive potential, frequency fixed, intensity fixed I1. Now after this we will vary the positive potential of the plate A gradually and measure the resulting photocurrent each time. So, after doing this experiment, it is found that the photoelectric current increases with increase in positive potential. Positive potential means accelerating potential. At some stage, for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes saturated. Students, if you have not subscribed the Sciacademy channel, please subscribe it so that you can get the notification of the upcoming videos. We wish to upload the video on regular interval of time. And if you like this video, please press the like button and share this with your friends so they can also learn about this video lecture. Further, if we increase the accelerating potential of plate, the photocurrent does not increase. That means it becomes saturated because all of the electrons emitted from the emitter C are getting collected by the plate A. Now, by just increasing the potential, there is not going to increase in the current. This maximum value of the photoelectric current is called the saturation current. The saturation current corresponds to the case when all the photoelectrons emitted by the emitter reach the collector plate A. Now we will apply a negative potential, that is also called the retarding potential, to the plate A with respect to the plate C and make it increasingly negative gradually. That means we will increase the negative potential slowly, and when the polarity is reversed, the electrons getting emitted from the emitter are now getting repelled back to the towards the emitter, and only the sufficiently energetic electrons are able to reach the collector plate A. The photocurrent is found to decrease rapidly until it drops to zero at a certain sharply defined critical value of the negative potential V naught on the plate A. For a particular frequency of the incident radiation, this minimum negative retarding potential V naught given to the plate A, for which the current stops or becomes zero is called the cutoff potential or stopping potential. So from the diagram, you can see that for the intensity I1, initially there was some photo current, and as we start increasing the positive potential difference, the current starts increasing, and after some time it gets maximum and becomes saturated. And when we reverse the polarity and start applying the negative potential between the plate C and A, then current starts decreasing, and slowly it becomes zero for a fixed negative potential, that is V naught. Further, if we are repeating the experiment by increasing the intensity of the incident radiation, the current starts increasing, again becomes saturated and attain the maximum value. And when we reverse the polarity, the current also becomes gradually zero for the certain retarding potential V naught. You can see that from the diagram, for all intensity of the incident radiation, the retarding potential is fixed. Students, similarly, we can repeat the experiment for the next intensity of the radiation I3, and we can see that the result is similar to the I1 I2, except there is a increase in the current. This shows that more electrons are being emitted per second for increasing the intensity of the radiation, but the stopping potential remains the same as that for the incident radiation of intensity I1 and I2. Thus, for a given frequency of the incident radiation, the stopping potential is independent of its intensity. So here we kept the frequency fixed and we are varying the potential only. And we see that stopping potential, that is retarding potential, is independent of its intensity. In other words, the maximum kinetic energy of the photoelectrons depends on the light source and the emitter plate material, that is work function, phi naught, but is independent of intensity of the radiation. Maximum kinetic energy of the photoelectrons depends on the light source and emitter plate material, that is work function, and is independent of the intensity of the incident radiation. So we see from this that the maximum kinetic energy can be given by E into V naught, where V naught is the retarding potential, and all the photoelectrons emitted from the metal do not have the same energy. Photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy K max. Students, now we will study the effect of frequency of incident radiation on the stopping potential, retarding potential, V naught. We suitably adjust the same intensity of light radiation at various frequencies and study the variation of photoelectric current with collector potential, plate potential. The resulting variation is shown in this figure. So we can see that we have kept incident radiation for the same intensity and we are varying the frequency of the radiation. We can see that as we are increasing the frequency, retarding potential is going to increase in the negative direction. That is, for more frequency, more retarding potential is needed to stop the highly energetic electrons to reach the collector. So we often different values of stopping potential but the same value of the saturation current for incident radiation of different frequency. The energy of the emitted electrons depends on the frequency of the incident radiation. The stopping potential is more negative for high frequency of the incident radiation. This implies that the greater the frequency of the incident light, greater is the maximum kinetic energy of the photoelectrons. Consequently, we need greater retarding potential to stop them completely. If we plot a graph between the frequency of the incident radiation and the corresponding stopping potential for different metals, we get a straight line. You can increase this backward, you can and see that they are intersecting the y-axis. From the diagram, you can see that for each metal there is a particular threshold frequency below which there is no emission of electron from the emitter, and graph also shows that stopping potential V naught varies linearly with the frequency of incident radiation for a given photosensitive material. So you can see that as we are increasing the frequency of incident radiation, stopping potential also increases linearly. So this is linear variation. And also I would like to mention one important thing is that the slope for each curve is fixed, and that is h by e. So further, there exists a certain minimum cutoff frequency nu naught for which the stopping potential is zero. The observation have two implications. First, maximum kinetic energy of the photoelectrons varies linearly with the frequency of the incident radiation but is independent of its intensity, as we also see previously. Second implication is for a frequency nu naught of the incident radiation lower than the cutoff frequency nu naught, no photoelectric emission is possible even if the intensity is large. So below this frequency for each metal, suppose we are taking this metal A. So there is a certain threshold frequency, cutoff frequency nu naught, and if the frequency of the incident radiation is below this nu naught, so there is no emission of the electron and the associated stopping potential is zero. So this minimum cutoff frequency is called the cutoff threshold frequency for a given material, given metal, and it is different for different metals. Different photosensitive materials respond differently to light. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelengths, that is different frequency. For example, ultraviolet light gives rise to photoelectric effect in copper, while green or red light doesn't, because green or red light used to have the higher wavelengths and lower frequency. Note that in all the above experiments, it is found that if the frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously. It is important to note that the process of emission of the photoelectrons is instantaneous, and that time is about 10 to the power minus 9 second or less than that. It is used to ask, the photoelectric emission is instantaneous or not? There is no time lag. It is instantaneous. The time lag is very, very small. It is 10 to the power minus 9 second or less than that. So we can summarize all the experimental features and observation described. First, for a given photosensitive material and frequency of the incident radiation. Of course, above the threshold frequency, the photoelectric current is directly proportional to the intensity of the incident light. That is, current is directly proportional to the intensity of the incident light, provided the frequency of incident radiation is more than the threshold frequency. Second, for a given photosensitive material and frequency of the incident radiation, saturation current is found to be proportional to the intensity of the incident radiation. You saw that when we are increasing the intensity, saturation current moves a little bit above the previous one, whereas the stopping potential is independent of its intensity, that remained same for all the intensity. Next, for a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation, which is used to call the threshold frequency, below which no emission of photoelectron is possible, no matter how intense the incident light is. Above the threshold frequency, the stopping potential or equivalently maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of the incident radiation. So, if the frequency of the incident radiation is more than the threshold frequency, then the energy of the emitted photoelectrons increases linearly with the frequency of the incident radiation, but is independent of its intensity. Figure on 11.5. It is independent of the intensity. Next, the photoelectric emission is an instantaneous process. As I told you, it takes only 10 to the minus 9 seconds or less than that also. There is no apparent time lag even when the incident radiation is made exceedingly dim. Even you are allowing the incident radiation intensity very small. In that case also, the emission of the photoelectric photoelectron from the emitter is instantaneous, provided the frequency of the incident radiation is more than the threshold frequency. And if you have not subscribed the Sai Academy channel till now, please subscribe the Sai Academy channel and share this video lecture with your friends. Thank you.